Hello, and welcome. I'm glad you're here. Tonight there's nowhere you need to go and nothing you need to solve. This is a quiet place to let your thoughts loosen their grip while we drift gently through the story of our home. Not the loud, hurried earth of headlines and schedules, but the slower one, the ancient one, the earth that turns patiently beneath you, whether you're paying attention or not. As you listen, there's no need to remember everything. Some ideas may settle softly in your mind. Others can pass by like distant waves, heard but not held. This isn't a lesson to master, it's a space to rest. In this video, we'll move through 100 calm, fascinating facts about the Earth. Its long journey through space, its deep history written in rock and water, the quiet systems that move air, shape land and sustain life without ever asking to be noticed. The oceans that absorb heat, the soil that breathes, the planet that has been slowly becoming itself for billions of years. If sleep finds you early, let it. If curiosity keeps you listening, that's welcome too. Just settle in, take a slow breath in and an even slower breath out. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, please consider liking and subscribing to the channel. It helps others find their way here too. And as we begin, it helps to remember this. The earth beneath you is very old, older than mountains, older than oceans, older than almost everything we can imagine. Its story stretches back billions of years, and that's where our first quiet fact begins. The earth beneath you is far older than almost anything the human mind is built to understand. Scientists estimate that our planet formed about 4.54 billion years ago, long before oceans, forests, or even solid ground as we know it today. In its earliest moments, Earth was a glowing sphere of molten rock, constantly struck by debris left over from the birth of the solar system. Over immense spans of time, gravity shaped it, heat slowly escaped, and the surface cooled enough for a crust to form. If Earth's entire history were compressed into a single day, modern humans would appear only in the final few seconds before midnight. Everything else, the formation of continents, the rise and fall of ancient oceans, the first life, the first extinctions, would happen long before we arrive. Nearly all of Earth's story unfolded without witnesses. This great age means that change is written into the planet itself. Mountains rise and erode, seas advance and retreat. Even the ground beneath your feet has been melted, broken and remade many times. Earth is not a static object. It is an ancient process, still unfolding. And from this deep sense of time, all other facts begin. From a distance, Earth appears round and complete, a smooth blue shape floating in space. But it is not a perfect sphere. Because the planet spins, it bulges slightly at the equator and flattens gently at the poles. This subtle shape is the result of rotation acting over billions of years, slowly redistributing mass outward where motion is fastest. The difference is small, only a matter of kilometers and completely imperceptible from the surface. Yet, it matters. This slight bulge affects how gravity behaves across the planet, how satellites orbit, and how measurements of Earth are made. You actually weigh a tiny bit less at the equator than at the poles, though the change is far too small to feel. What's remarkable is how quietly this imperfection exists. Earth does not resist motion. It responds to it. The planet yields just enough to accommodate the forces acting upon it, adjusting its shape without drama. Even something as solid as Earth is shaped by movement. Its form is not fixed, but gently molded by time, rotation, and balance. Earth completes one full rotation every 24 hours, But not every place on the planet moves at the same speed. At the equator, Earth spins at roughly 1,000 miles per hour. As you move closer to the poles, that speed gradually decreases until at the poles themselves, rotation becomes a slow turning in place. This happens because points along the equator have a much longer distance to travel during each rotation. Like riders on a spinning carousel, those farther from the center move faster than those closer in. The planet turns as a single body, but the experience of that motion changes with latitude. This difference quietly shapes the world. It influences wind patterns, ocean currents, and the paths of storms. Air moving across Earth is gently deflected by rotation, creating the great circulating systems that move heat and moisture around the globe. None of this is felt directly. Even at tremendous speeds, the motion is smooth, constant, and shared by everything around you. The planet spins, the atmosphere spins with it, and life moves along without resistance. Motion, when steady enough, feels like rest. Earth's rotation feels timeless, but it is slowly changing. Over millions of years, the planet's spin has been gradually slowing down, making each day slightly longer than the one before. Long ago, Earth rotated faster and days were shorter. Hundreds of millions of years ago, a full day lasted only about 22 hours. The primary cause of this slowdown is the Moon. As the Moon orbits Earth, its gravity creates tides not only in the oceans, but in the solid body of the planet itself. These tidal forces act like a gentle brake, transferring rotational energy from Earth to the Moon and pushing the Moon slowly farther away. The change is incredibly small, about 2 milliseconds per century. No living person could ever notice it, but over deep time, it accumulates. Time stretches almost imperceptibly, like a clock that loses a fraction of a second across ages. This slow shift reminds us that even the most familiar rhythms are not fixed. Day and night, waking and sleeping are part of a living system still evolving. Earth keeps time patiently. The seasons exist because Earth is tilted. Its axis leans about 23.5 degrees as it travels around the Sun. This tilt determines how sunlight spreads across the planet throughout the year, shaping temperature, daylight, and climate. When the northern hemisphere tilts toward the Sun, sunlight strikes more directly and days grow longer. Summer arrives. At the same time, the southern hemisphere tilts away, receiving less direct sunlight and experiencing winter. 6 months later, the pattern reverses. It is not Earth's distance from the Sun that causes the seasons. That distance changes only slightly during the year. The tilt alone creates the slow-breathing rhythm of warming and cooling, growth and rest. Without this tilt, Earth would be far more uniform. There would be little seasonal contrast, fewer migrations, fewer cycles of renewal. The planet would feel flatter, less dynamic. Instead, Earth leans into its orbit, allowing light to move gently across its surface like a tide, returning again and again. Earth's tilt is not only important, it is unusually stable. This stability is largely due to the Moon. Without the Moon's gravitational influence, Earth's axis would wobble far more chaotically over time, swinging between extreme angles. Such instability would lead to dramatic climate shifts, sudden changes in seasons, and conditions that might make complex life difficult to sustain. Instead, the Moon acts like a steadying presence, keeping Earth's tilt within a narrow, life-friendly range for billions of years. This quiet partnership has allowed ecosystems time to adapt and evolve. Seasons remain predictable. Climates shift slowly rather than violently. Life is given time. The Moon also shapes ocean tides, slows Earth's rotation, and subtly influences the planet's interior. But its stabilizing effect on Earth's tilt may be one of its most important roles. It does all of this silently from a distance without intention or awareness, a simple result of gravity and motion. The moon does not guide Earth, it steadies it, and in that steadiness, life found room to grow. Earth does not travel around the sun in a perfect circle. Its orbit is slightly elliptical, forming a gentle oval shape. Over the course of a year, Earth moves a little closer to the sun and then a little farther away again. This change in distance is small and does not cause the seasons, but it does subtly influence how much solar energy Earth receives at different times of the year. Interestingly, Earth is closest to the Sun during the Northern Hemisphere's winter. The orbit is smooth, stable, and remarkably consistent. For billions of years, Earth has followed nearly the same path, held in place by gravity and momentum. It neither drifts away nor falls inward. This balance allows life to persist. Too much variation would create chaos. Too little might create stagnation. Earth's orbit rests comfortably between the two. Each year, the planet completes this quiet loop, again and again without pause. A gentle curve through space that repeats with calming reliability. Motion does not always mean disruption. Sometimes it means reassurance. As Earth orbits the Sun, it travels through space at roughly 67,000 miles per hour. This speed is difficult to imagine because everything around you moves with it. The air, the oceans, the ground beneath your feet all share the same motion. There is no sensation of rushing wind or vibration. The movement is smooth, constant, and shared, creating the feeling of stillness. Motion becomes invisible when it is steady enough. At the same time, the Sun itself is moving through the Milky Way galaxy, carrying Earth and the rest of the solar system along with it. We are part of multiple journeys layered together, each one vast, each one silent. Even now, as you rest, you are moving faster than any machine humans have ever built. And yet, the experience is calm. This is one of Earth's quiet gifts. It allows enormous motion without disturbance. It carries life gently through space, protecting it from the feeling of speed. Sometimes the fastest journeys feel like rest. Earth is not only orbiting the Sun. Together with the entire solar system, it also orbits the center of the Milky Way galaxy. One complete journey around the galactic center takes roughly 230 million years. This vast span of time is known as a cosmic year. Since Earth formed, it has completed only about 20 of these galactic orbits. Dinosaurs lived during different galactic positions than we do now. Entire continents shifted during a single cosmic year. The scale of this motion is immense. Stars drift, spiral arms rotate, gravity binds everything together in slow, graceful motion. From within the system, the movement is almost impossible to perceive, yet it is always happening. Earth follows the Sun follows the galaxy moves among others. We live inside a turning structure far larger than daily experience allows us to imagine, and still, night arrives gently. Even the Milky Way is not still. It drifts through the universe, pulled by the gravity of other galaxies and immense structures beyond our view. The Sun, the planets, and Earth itself are all passengers in this larger motion. There is no single point of rest. Everything moves in relation to everything else. Motion is layered, overlapping, continuous. And yet, from where you are now, it feels like stillness. Earth turns, the solar system travels, the galaxy drifts. But here, breath slows, muscles soften, awareness settles. This contrast is part of what makes Earth feel safe. Vast motion held inside gentle experience, enormous journeys unfolding beneath calm nights. The planet has been moving like this for billions of years, carrying oceans, forests, creatures, and now sleeping minds along with it. It does not rush, it does not hesitate, and as Earth continues its quiet journey through space, its deeper story begins to unfold, written not in motion alone, but in time itself. As Earth continued its long journey through space, something important remained absent for a very long time: complex life. For most of Earth's 4.54 billion year history, the planet was inhabited only by simple organisms. Single-celled life dominated the oceans for billions of years, quietly shaping the environment long before animals or plants appeared. These early forms of life were small, resilient, and remarkably patient. They did not build forests or leave obvious traces. Instead, they worked slowly, changing the chemistry of the oceans and atmosphere molecule by molecule. Oxygen, which now fills the air you breathe, was once rare and even deadly to many early organisms. If Earth's history were written as a book, nearly every page would describe a world without trees, without insects, without anything that looks familiar. Complex life arrives very late in the story, only after countless invisible changes had prepared the way. This long prelude reminds us that life does not rush. It experiments, it waits, and when conditions are finally right, it changes the planet forever. That transformation began on a world that was once far more hostile than the Earth we know today. In its earliest days, Earth was not a gentle place. It was a world of fire. The surface was largely molten, heated by constant impacts from space and intense internal energy left over from formation. There were no oceans, no atmosphere like today's, and no stable ground to stand on. Volcanoes dominated the landscape, releasing gases that would eventually form the atmosphere. Meteorites struck frequently, reshaping the surface again and again. Heat radiated from the planet's interior, making the environment unstable and extreme. Life as we understand it could not survive under these conditions. Yet even in this chaos, Earth was slowly preparing itself. As impacts decreased and heat escaped into space, the surface began to cool. A solid crust formed, gases accumulated, water vapor condensed. This transformation took hundreds of millions of years. There was no sudden moment when Earth became calm. Instead, it cooled gradually, step by step, moving from violent beginnings towards stability. The planet we rest on today is the result of that slow cooling, a reminder that even the most peaceful worlds can begin in fire. And once Earth cooled enough, something remarkable began to collect on its surface. As Earth continued to cool, water began to appear. At first, it existed only as vapor in the atmosphere, released by volcanic activity and delivered by icy objects from space. Over time, temperatures dropped enough for that vapor to condense. Rain fell for ages. Not gentle rain, but relentless precipitation that slowly filled low places on the surface. The first oceans began to form more than 4 billion years ago, covering much of the planet. These early oceans were warm and mineral-rich, very different from today's seas. Yet they provided something essential: stability. Water absorbs heat and moderates temperature, helping Earth settle into a more balanced state. Within these ancient waters, chemistry grew more complex, molecules interacted, energy flowed, and eventually life emerged. The oceans became Earth's memory, holding traces of everything that came after. Even now they regulate climate, support life, and quietly shape the planet. The appearance of oceans marked a turning point. Earth was no longer just cooling, it was becoming a place where change could last. And beneath those waters, the surface of the planet itself began to move. Earth's surface is not a single unbroken shell. It is divided into large pieces called tectonic plates that float atop the slowly moving mantle below. These plates shift, collide, pull apart, and slide past one another over immense spans of time. This motion is called plate tectonics, and it has been reshaping Earth for billions of years. Continents drift across the planet. Oceans open and close. Mountains rise where plates collide, and valleys form where they separate. The movement is incredibly slow, often only a few centimeters per year. But over millions of years, it transforms the face of the planet. Land that was once near the equator may travel toward the poles. Shallow seas may become dry land. Entire continents can merge or break apart. This slow motion helps regulate Earth's climate by recycling carbon, shaping ocean currents, and renewing the surface. It prevents the planet from becoming geologically stagnant. Earth is alive in this quiet way. Not still, not rigid, but constantly rearranging itself beneath our feet. And sometimes, those moving plates come together to form something much larger. Over Earth's long history, continents have not always existed in their current positions. At several points, most or all of Earth's land masses merged into enormous supercontinents. The most famous of these is Pangaea, which existed about 300 million years ago. Before Pangaea and after it, other supercontinents formed and broke apart as well. This cycle of assembly and separation repeats over hundreds of millions of years, driven by the slow motion of tectonic plates. When continents merge, ocean currents change, climate patterns shift, life adapts or disappears. When continents break apart, new coastlines form, seas open, and ecosystems diversify. These changes are never sudden. They unfold so slowly that life experiences them as background conditions rather than events. Forests grow where deserts once lay. Ice forms where jungles once thrived. The continents you know today are temporary arrangements. They are snapshots in an ongoing story, and as land rearranged itself again and again, Earth quietly preserved clues from its earliest moments. The oldest objects ever found on Earth are tiny crystals called zircons. Some of these minerals are more than 4.4 billion years old, nearly as old as the planet itself. They formed when Earth was still young, locking away chemical information like time capsules. These ancient zircons tell scientists that liquid water existed surprisingly early in Earth's history. They suggest that crust formed and stabilized sooner than once believed, even while the planet was still cooling. Zircons are incredibly durable. They survive heat, pressure, and erosion. Long after the rocks around them melt or break apart, the crystals remain, carrying memories of Earth's earliest surface. Most of the planet's original crust has been recycled by tectonic activity, but these tiny minerals endured, offering rare glimpses into a vanished world. They remind us that Earth does not remember everything. Much of its past is gone forever. What remains is fragmentary, scattered, and precious. And because so little survives, the record of ancient life itself is even rarer. Despite the vast amount of life that has existed on Earth, fossils are uncommon. Most organisms never leave behind any trace at all. To become a fossil, an organism must die under very specific conditions, often being quickly buried by sediment that protects it from decay. Soft-bodied creatures almost always vanish without a record. Even hard shells and bones are usually destroyed by scavengers, erosion, or geological recycling. Over time, heat and pressure can erase fossils completely. What we know of ancient life comes from a tiny fraction of what once lived. The fossil record is incomplete, uneven, and full of gaps. Entire ecosystems may have existed without leaving a single fossil behind. And yet, the fossils we do find tell powerful stories. They show gradual change, sudden loss, and unexpected survival. They reveal how life responds to shifting environments. The absence of fossils is itself a reminder of Earth's constant motion. The planet does not preserve easily. It reshapes, recycles, and moves on. Sometimes that reshaping happens catastrophically. Throughout Earth's history, life has faced repeated crises. Scientists have identified at least 5 major mass extinction events, periods when a large percentage of species disappeared in a relatively short time. These extinctions were caused by different forces: massive volcanic eruptions, asteroid impacts, rapid climate shifts, changes in ocean chemistry. Each event reshaped life on Earth. The most severe, the Permian extinction, wiped out more than 90% of marine species. Forests vanished. Ecosystems collapsed. The planet entered a long period of recovery. Mass extinctions are not just endings, they are also transitions. After each one, life returned in new forms. Survivors diversified. New species filled empty ecological roles. Earth does not protect life from loss, but it does provide opportunities for renewal. Over time, complexity returns, often in unexpected ways. These events remind us that stability is never permanent. Change is woven into Earth's story at every scale, and after each collapse, something new quietly begins to grow. After every mass extinction, Earth did not remain barren. Life returned, slowly at first, then with increasing diversity. Recovery often took millions of years, but it always came. Small, adaptable organisms tended to survive best. From these survivors, new ecosystems emerged. Fish diversified after ancient ocean extinctions. Mammals expanded after the dinosaurs disappeared. Forests returned after long periods of devastation. The new life was never the same as what came before. Each recovery reshaped the planet's living fabric, creating worlds that no previous age had seen. This pattern shows something important about Earth. It does not aim to preserve specific species. Instead, it supports processes. Given time, energy, and chemistry, life reorganizes itself. Recovery is not fast, it is not gentle, but it is persistent. Earth allows loss, but it also allows renewal. Again and again, the planet has proven capable of supporting life even after profound disruption. And these cycles of loss and recovery were often driven by something even larger. Over billions of years, Earth's climate has never stayed the same. The planet has experienced periods far warmer than today, with tropical forests near the poles, and periods far colder, when ice sheets covered much of the surface. These shifts were driven by changes in greenhouse gases, continental positions, ocean circulation, volcanic activity, and even subtle variations in Earth's orbit. Climate responded slowly at times and rapidly at others. Life adapted to these changes, migrated, or vanished. New ecosystems formed. Old ones faded away. Climate shaped evolution as much as biology itself. What feels stable to us is only a brief moment in a long sequence of change. Earth's climate has always moved, adjusted, and responded to forces both internal and external. This long history reminds us that the planet is dynamic, not fixed. Balance is temporary, motion is constant. And beneath these shifting climates, deeper processes continued quietly, shaping the planet from within. Beneath Earth's shifting climate and changing surface lies a layered interior, hidden from view but essential to everything above it. The planet is structured like a set of nested shells, beginning with the thin crust, then the thick mantle, followed by the outer core, and finally the inner core at the center. The crust is where continents rest and oceans spread. It is thin compared to the rest of the planet, more like the skin of an apple than a solid shell. Below it lies the mantle, extending thousands of kilometers downward, made of hot rock that behaves neither fully solid nor fully liquid. Deeper still is the core. The outer core is molten metal, while the inner core remains solid due to immense pressure. These layers formed as Earth cooled and heavier elements sank toward the center. This internal structure is not static. Heat moves upward, material circulates, energy flows slowly from the deep interior to the surface. Earth is not hollow or inert. It is active from the inside out, and this internal activity sets the stage for motion beneath the crust. The mantle makes up most of Earth's volume, yet it rarely comes to mind. Though it is solid rock, it behaves in an unusual way. Under immense heat and pressure, mantle rock can slowly flow, bending and shifting over millions of years. This movement is incredibly slow, often measured in centimeters per year, but over deep time, it becomes powerful. Mantle convection transfers heat from Earth's interior toward the surface, driving the motion of tectonic plates above. You might imagine the mantle as thick honey or soft wax, yielding gradually under force. It does not rush. It does not fracture easily. It responds patiently to energy and gravity. This slow circulation carries heat upward and cooler material downward, creating vast convection cells that operate continuously beneath the crust. Without this motion, Earth's surface would eventually become rigid and lifeless. The mantle connects Earth's deep interior to its surface. It allows energy to move, continents to drift, and mountains to rise. And all of this motion is powered by heat, quietly generated far below. Earth's interior remains hot not only because of its fiery beginnings, but also because of ongoing processes deep within the planet. When Earth first formed, collisions and gravitational compression generated enormous heat. Much of that heat remains trapped inside, slowly escaping over time. In addition, radioactive elements such as uranium, thorium, and potassium are scattered throughout Earth's interior. As these elements decay, they release heat. This radioactive decay continues steadily, providing a long-lasting internal energy source. Together, leftover heat and radioactive decay keep Earth's interior warm enough to sustain mantle movement, volcanic activity, and a liquid outer core. Without this heat, Earth would have cooled completely long ago. This internal warmth does not blaze outward. It seeps upward slowly, shaping the planet without sudden violence most of the time. It is patient energy, working across immense spans of time. The surface may feel solid and still, but deep below, Earth remains warm and active. That heat eventually concentrates toward the planet's center, where the densest materials reside. At Earth's center lies its core, composed primarily of iron and nickel. These heavy elements sank inward during the planet's early history, pulled by gravity as Earth differentiated into layers. The core is enormous. It is about as wide as the planet Mars, yet completely hidden beneath thousands of kilometers of rock. Despite this distance, its influence reaches the surface. Iron dominates the core because it is dense and abundant. Nickel accompanies it, strengthening the metallic mixture. Together, they form the foundation of Earth's magnetic field and contribute to the planet's overall mass. The core's composition tells us something about Earth's origins. The materials that built the planet came from ancient stellar explosions, forged long before the sun existed. Earth's deepest layers are made of stardust, compressed and transformed by gravity and heat. The core is not directly accessible, but its presence is felt everywhere. It anchors the planet, powers internal processes, and quietly shapes life above. And within the core itself, conditions differ dramatically between its outer and inner regions. Beneath Earth's shifting climate and changing surface lies a layered interior, hidden from view but essential to everything above it. The planet is structured like a set of nested shells, beginning with the thin crust, then the thick mantle, followed by the outer core, and finally the inner core at the center. The crust is where continents rest and oceans spread. It is thin compared to the rest of the planet, more like the skin of an apple than a solid shell. Below it lies the mantle, extending thousands of kilometers downward, made of hot rock that behaves neither fully solid nor fully liquid. Deeper still is the core. The outer core is molten metal, while the inner core remains solid due to immense pressure. These layers formed as Earth cooled and heavier elements sank toward the center. This internal structure is not static. Heat moves upward, material circulates, energy flows slowly from the deep interior to the surface. Earth is not hollow or inert. It is active from the inside out, and this internal activity sets the stage for motion beneath the crust. The mantle makes up most of Earth's volume, yet it rarely comes to mind. Though it is solid rock, it behaves in an unusual way. Under immense heat and pressure, mantle rock can slowly flow, bending and shifting over millions of years. This movement is incredibly slow, often measured in centimeters per year, but over deep time, it becomes powerful. Mantle convection transfers heat from Earth's interior toward the surface, driving the motion of tectonic plates above. You might imagine the mantle as thick honey or soft wax, yielding gradually under force. It does not rush. It does not fracture easily. It responds patiently to energy and gravity. This slow circulation carries heat upward and cooler material downward, creating vast convection cells that operate continuously beneath the crust. Without this motion, Earth's surface would eventually become rigid and lifeless. The mantle connects Earth's deep interior to its surface. It allows energy to move, continents to drift, and mountains to rise. And all of this motion is powered by heat, quietly generated far below. Earth's interior remains hot not only because of its fiery beginnings, but also because of ongoing processes deep within the planet. When Earth first formed, collisions and gravitational compression generated enormous heat. Much of that heat remains trapped inside, slowly escaping over time. In addition, radioactive elements such as uranium, thorium, and potassium are scattered throughout Earth's interior. As these elements decay, they release heat. This radioactive decay continues steadily, providing a long-lasting internal energy source. Together, leftover heat and radioactive decay keep Earth's interior warm enough to sustain mantle movement, volcanic activity, and a liquid outer core. Without this heat, Earth would have cooled completely long ago. This internal warmth does not blaze outward. It seeps upward slowly, shaping the planet without sudden violence most of the time. It is patient energy, working across immense spans of time. The surface may feel solid and still, but deep below, Earth remains warm and active. That heat eventually concentrates toward the planet's center, where the densest materials reside. At Earth's center lies its core, composed primarily of iron and nickel. These heavy elements sank inward during the planet's early history, pulled by gravity as Earth differentiated into layers. The core is enormous. It is about as wide as the planet Mars, yet completely hidden beneath thousands of kilometers of rock. despite this distance, its influence reaches the surface. Iron dominates the core because it is dense and abundant. Nickel accompanies it, strengthening the metallic mixture. Together, they form the foundation of Earth's magnetic field and contribute to the planet's overall mass. The core's composition tells us something about Earth's origins. The materials that built the planet came from ancient stellar explosions, forged long before the Sun existed. Earth's deepest layers are made of stardust, compressed and transformed by gravity and heat. The core is not directly accessible, but its presence is felt everywhere. It anchors the planet, powers internal processes, and quietly shapes life above. And within the core itself, conditions differ dramatically between its outer and inner regions. The Sun constantly releases streams of charged particles into space. When these particles reach Earth, they encounter the magnetic field, which redirects most of them away from the planet. This protection prevents significant loss of atmosphere and shields life from harmful radiation. Without it, Earth might resemble Mars, which lost much of its atmosphere after its magnetic field weakened. Sometimes particles slip through near the poles, creating auroras. These shimmering lights are visible signs of the magnetic field interacting with solar energy. Most of the time, however, the protection is silent and unseen. Life continues without awareness of the danger being deflected above. This invisible shield has allowed complex organisms to thrive on land, exposed to sunlight without being destroyed by it. Earth does not guard life intentionally. It simply behaves according to physics. Yet the result is safety. And from this protection, energy continues to escape slowly from within the planet. Earth's internal heat does not remain trapped forever. It escapes gradually through the crust, most visibly through volcanoes and hydrothermal vents. Volcanoes release molten rock, gas and heat from deep below, reshaping the surface and renewing it with fresh material. Hydrothermal vents, often hidden beneath oceans, allow heat and minerals to flow into surrounding water. These outlets prevent pressure from building endlessly within the planet. They are release valves, allowing Earth to cool slowly rather than violently. Volcanic activity also contributes gases to the atmosphere and minerals to the surface, influencing climate and supporting ecosystems over long timescales. Though eruptions can be destructive locally, they are part of Earth's long-term balance. They redistribute energy, recycle materials, and connect the deep interior to the surface. The planet breathes through these openings, exhaling heat accumulated over billions of years. And with that heat shaping the surface, Earth's outer layers continue their slow, restless motion. As Earth releases heat from within, its outer shell responds. The crust is broken into large slabs called tectonic plates, and these plates do not rest on a rigid foundation. Instead, they float atop the slowly moving mantle beneath them. This floating is not like ice on water, but more like thick wood resting on soft clay. The plates are rigid compared to the mantle, yet they are carried along by its slow, persistent flow. Over millions of years, this motion carries continents across the planet. Some plates move apart, creating new crust. Others collide, forcing land upward or downward. Still others slide past one another, storing energy that may later be released as earthquakes. This movement is constant but nearly imperceptible. No sound, no vibration, just steady motion measured in centimeters per year. Earth's surface feels solid, but it is not fixed. It drifts, reshapes and rearranges itself over deep time. And where these drifting plates meet, the planet often releases its tension in sudden, powerful ways. Earthquakes are the result of stress building up where tectonic plates interact. Most occur along plate boundaries, the edges where plates collide, separate, or slide past one another. As plates move, they do not glide smoothly. Friction locks them together, allowing pressure to accumulate. Eventually, the stress becomes too great and the plates slip. Energy is released as seismic waves that ripple through the earth. These waves travel outward, shaking the ground and reminding us that motion is always present beneath the surface. Some earthquakes are small and pass unnoticed. Others reshape landscapes and alter coastlines. The planet does not choose when or where earthquakes occur. They are the natural result of ongoing movement. Earth relieves tension the only way it can. Even after an earthquake ends, plates continue to move. Stress begins to build again, slowly and quietly. This cycle of tension and release is part of Earth's long-term balance, and in some places, plate interactions go even deeper, carrying crust back into the planet itself. At certain plate boundaries, one tectonic plate slides beneath another. These regions are called subduction zones, and they play a crucial role in recycling Earth's surface. Oceanic crust is denser than continental crust. When they meet, the oceanic plate sinks into the mantle below, pulled downward by gravity. As it descends, it heats up, melts, and releases fluids that help generate magma. This process prevents ocean crust from piling up endlessly. Instead of accumulating forever, it is returned to the planet's interior, where its materials can be reused. Subduction zones are often marked by deep ocean trenches, powerful earthquakes, and volcanic arcs. They are among the most geologically active regions on Earth, yet the recycling itself is slow. A piece of crust may take tens of millions of years to complete its journey downward. Earth does not waste material, it reprocesses it over and over again. And sometimes when plates meet without subduction, the result is not destruction, but uplift. When two continental plates collide, neither easily sinks beneath the other. Instead, the crust crumples and thickens, slowly rising to form mountain ranges. This process is gradual. There is no sudden lifting of peaks. Over millions of years, rock layers fold, fault, and stack upon one another, pushed upward by relentless pressure. The Himalayas are a famous example. They formed when the Indian plate collided with the Eurasian plate, a process that is still ongoing today. The mountains continue to rise, even as erosion wears them down. Mountain building is a balance between uplift and erosion. Wind, water, and ice sculpt the rising land, shaping valleys and peaks. These towering landscapes are records of deep forces acting slowly and persistently. Mountains influence climate by redirecting winds and rainfall. They shape ecosystems and river systems. They feel timeless, yet they are temporary, born from motion and destined to change. And nowhere is Earth's restless surface more visible than beneath the oceans. The Himalayas are among the youngest and tallest mountain ranges on Earth, and they are still growing today. The Indian tectonic plate continues to push northward into the Eurasian plate, forcing rock upward. This collision began around 50 million years ago and has not stopped. Each year, the mountains rise by a few millimeters, even as erosion slowly wears them down. Earthquakes frequently occur in this region, releasing stress from the ongoing collision. Rivers carve deep valleys through rising rock, carrying sediment toward the sea. The Himalayas influence weather patterns across Asia, shaping monsoons and climate over vast areas. They also store enormous amounts of ice and snow, feeding major river systems. These mountains appear permanent and immovable, yet they are the result of slow, continuous change. Their height is not a finished product. It is a moment in an ongoing process. And while mountains rise on land, an even longer mountain chain stretches unseen across the ocean floor. Hidden beneath the oceans lies the longest mountain range on Earth. Mid-ocean ridges stretch for more than 40,000 miles, winding around the planet like seams. These ridges form where tectonic plates move apart. As they separate, molten rock rises from below, cools and solidifies, creating new oceanic crust. This process slowly pushes older crust outward on either side, expanding ocean basins over time. The Atlantic Ocean, for example, continues to widen as new crust forms along its central ridge. Mid-ocean ridges are sites of constant creation. Earth's surface is being renewed there every day, though the motion is far too slow to notice. Hydrothermal vents often dot these ridges, supporting unique ecosystems that rely on chemical energy instead of sunlight. The ocean floor is not flat or quiet. It is active, growing, and reshaping itself continuously. And where crust is created in some places, it must be destroyed in others. Encircling the Pacific Ocean is a vast zone of geological activity known as the Ring of Fire. This region contains about 75% of Earth's active volcanoes and experiences frequent earthquakes. The Ring of Fire exists because many tectonic plates meet around the edges of the Pacific. Subduction zones dominate, pulling oceanic crust downward and generating magma. Volcanoes in this region can erupt explosively, releasing ash, gas, and lava. Over time, these eruptions build islands, mountains, and entire landscapes. Though destructive at times, volcanic activity also creates fertile soils and new land. It reshapes coastlines and influences climate on both local and global scales. The Ring of Fire is not a single structure, but a collection of processes linked by plate motion. It reminds us that Earth's surface is not evenly active. Some regions are quieter, while others release energy more dramatically. And sometimes, volcanic activity occurs in places far from plate boundaries. In some parts of the world, volcanoes erupt beneath thick ice sheets or glaciers. These subglacial eruptions occur in places like Iceland and Antarctica, where fire meets ice. When magma rises beneath ice, it melts its way upward, creating pockets of water trapped under enormous pressure. The interaction can produce explosive eruptions or sudden floods when meltwater escapes. These eruptions shape the landscape in unusual ways, forming flat-topped mountains and ridges made of rapidly cooled lava. Subglacial volcanoes also influence climate and ice stability. Heat from below can weaken ice sheets, while ash deposited on ice reduces reflectivity and increases melting. These interactions show how Earth's systems overlap. Fire affects ice, ice affects water, water reshapes land. Nothing on Earth operates in isolation, and sometimes the energy released by these processes can subtly affect the planet's motion itself. Large earthquakes can subtly alter Earth's rotation. When massive amounts of rock shift during an earthquake, they redistribute Earth's mass, changing how the planet spins. These changes are extremely small. An earthquake might shorten or lengthen the day by fractions of a microsecond. The effect is far beyond human perception. Still, it demonstrates how interconnected Earth's systems are. A sudden shift in crust can influence the motion of the entire planet. Earth behaves like a spinning figure skater. When mass moves closer to the axis, rotation speeds up slightly. When it moves outward, rotation slows. These adjustments are tiny, but measurable with precise instruments. The planet absorbs these changes without disruption. Day and night continue. Seasons remain steady. Earth flexes, adjusts, and carries on. And sometimes Earth's internal activity influences not just motion, but temperature as well. When large volcanoes erupt, they can influence Earth's climate by injecting ash and sulfur-rich gases into the upper atmosphere. These particles reflect sunlight back into space, reducing the amount of energy reaching the surface. This effect can cause temporary cooling that lasts months or even years. After the eruption of Mount Pinatubo in 1991, global temperatures dropped slightly for a short period. Volcanic cooling does not last forever. Particles eventually settle out of the atmosphere, and temperatures return to previous patterns. Still, these events show how Earth's internal processes can reach into the atmosphere and influence climate. Volcanoes remind us that the planet's systems are linked from core to sky. Earth breathes heat outward, sometimes gently, sometimes forcefully. And with that connection between land, sea, and air established, our attention naturally turns toward the planet's vast oceans, where much of Earth's story continues quietly below the surface. After shaping the land with fire and motion, Earth is mostly covered by water. About 71% of the planet's surface lies beneath the oceans, making Earth unmistakably a water world. From space, this dominance is obvious, with deep blues wrapping around continents like a living skin. The ocean's smooth temperature extremes absorb heat and circulate energy across the globe. They are not just features on Earth's surface, but fundamental systems that regulate climate and weather. Without them, Earth would be far harsher and far less stable. Most coastlines are shaped by the slow, rhythmic movement of waves. Over time, water wears rock into sand, reshaping land grain by grain. What feels solid is constantly being softened. The presence of so much water has influenced every chapter of Earth's story, from the origin of life to the movement of continents. And while the surface of the ocean is familiar, the true scale of Earth's water world extends far deeper than we usually imagine. When we think of life on Earth, we often picture forests, grasslands, and animals moving across land. But most of Earth's living space exists underwater. The oceans provide a vast three-dimensional environment where life can thrive at many depths. From sunlit surface waters to dark abyssal plains, organisms occupy layers stacked one above another. Even small changes in depth can create entirely different habitats, shaped by light, pressure, and temperature. Because of this vertical dimension, the ocean contains far more habitable volume than land. Countless species live suspended in water, drifting, swimming, or anchoring themselves to the sea floor. Many of these organisms are small, fragile, or translucent, adapted to a world where buoyancy replaces solid ground. Life here moves slowly, conserving energy in a stable environment. The ocean is not empty space between continents. It is Earth's largest living system, quiet and expansive, and much of this living space lies far beyond our reach or direct observation. Despite covering most of the planet, the deep ocean remains one of Earth's least explored regions. Much of the seafloor lies thousands of meters below the surface, hidden beneath darkness and immense pressure. Exploring these depths is difficult and costly. Specialized submersibles and remote vehicles are required, and even then, only small areas can be observed at a time. As a result, large portions of the ocean floor have never been seen directly. Each expedition often reveals new species, unfamiliar landscapes, and unexpected ecosystems. Creatures adapted to darkness, cold, and pressure move slowly through these environments, many unlike anything found on land. The deep ocean reminds us that Earth still holds mysteries. Even on our own planet, vast regions remain unknown. This unseen world plays an important role in global systems, storing heat, cycling nutrients and supporting life in ways we are only beginning to understand. And within these depths lie features even more dramatic than those found on land. Earth's oceans contain trenches so deep that they surpass the height of the tallest mountains. The Mariana Trench, the deepest known point, plunges nearly 11 kilometers below the ocean's surface, deeper than Mount Everest rises above sea level. These trenches form at subduction zones, where one tectonic plate sinks beneath another. Over millions of years, this process pulls the seafloor downward, creating long, narrow depressions. At such depths, pressure is immense. Water presses with the weight of thousands of tons on every square meter. Temperatures are low. Light does not reach these regions at all, and yet life exists there. Strange organisms survive in conditions once thought impossible, adapted to pressure and darkness. Ocean trenches remind us that Earth's extremes are not limited to land. Some of the planet's most dramatic features lie hidden beneath miles of water, and the deeper you go, the more pressure shapes everything that lives there. As you descend into the ocean, pressure increases quickly. For every 10 meters of depth, pressure rises by about 1 additional atmosphere. By the time you reach the deepest trenches, the pressure is hundreds of times greater than at the surface. This pressure affects everything. Air spaces collapse, materials compress. Most surface organisms could not survive even a fraction of that depth. Deep sea creatures are built differently. Their bodies often lack rigid, air-filled cavities. Their tissues are flexible. Their chemistry is adapted to pressure that would crush most life. Pressure slows movement and shapes behavior. Many deep-sea animals drift gently, conserving energy in a stable environment where sudden motion is costly. Despite the harsh conditions, pressure also brings stability. Temperatures remain constant. Storms and surface chaos never reach the deep. The ocean becomes quieter, darker, and calmer with depth. And in that calm darkness, some life thrives without sunlight at all. In the deep ocean, far from sunlight, hydrothermal vents release hot, mineral-rich water from beneath the seafloor. These vents form along mid-ocean ridges and tectonic boundaries, where Earth's internal heat escapes. Around these vents, entire ecosystems flourish. Instead of relying on photosynthesis, life here depends on chemosynthesis. Microbes use chemical energy from sulfur and other compounds to produce food. Larger organisms, such as tube worms and clams, form partnerships with these microbes, allowing complex life to exist in total darkness. These ecosystems show that sunlight is not the only foundation for life. Energy from within Earth itself can sustain living systems. Hydrothermal vents may resemble environments where life first emerged on Earth, and possibly where life could exist on other worlds. They reveal a planet that provides multiple pathways for life to persist. And beyond supporting life, the oceans also act as massive conveyors of energy. The oceans are constantly in motion. Vast currents move water around the planet, redistributing heat from warm regions toward cooler ones. Surface currents are driven by winds and Earth's rotation, while deep currents are driven by differences in temperature and salinity. Together, they form a global circulation system often called the ocean conveyor belt. This circulation helps regulate climate by smoothing temperature extremes. Warm water carried poleward releases heat into the atmosphere, while cold water returns toward the equator. Without these currents, some regions would be far hotter, others far colder. Weather patterns would shift dramatically. Ocean currents move slowly but persistently, taking centuries to complete a full global loop. They operate quietly, beneath storms and waves, shaping climate over long time scales. The ocean does not rush, it carries heat patiently, and one particular current plays an outsized role in shaping climates far from its origin. The Gulf Stream is a powerful ocean current that carries warm water from the Gulf of Mexico across the Atlantic Ocean toward Europe. As it travels, it releases heat into the atmosphere, moderating temperatures along the way. Because of the Gulf Stream, parts of Europe experience milder winters than other regions at similar latitudes. Cities that might otherwise be frozen remain relatively temperate. This warmth influences ecosystems, agriculture, and human settlement. It shapes weather patterns and supports life far from the tropics. The Gulf Stream is driven by wind patterns and differences in water density. It is part of the larger ocean circulation system that connects all the world's seas. Though strong, the current is not permanent or unchanging. Its speed and path can shift in response to climate conditions. Still, it continues its steady flow, carrying heat across oceans. And as oceans move heat around the planet, they also quietly absorb it. As Earth warms, much of the excess heat does not remain in the atmosphere. Instead, the oceans absorb it. Water has a high heat capacity, meaning it can store large amounts of energy without large temperature changes. This buffering effect helps slow atmospheric warming and stabilizes climate in the short term. The ocean acts like a thermal reservoir, quietly taking in heat year after year. Most of this heat is stored in the upper layers, but some penetrates deeper, carried by currents. Once stored, it can remain in the ocean for decades or longer. This absorption is not without consequences. Warmer oceans expand, contribute to sea level rise, and affect marine ecosystems. Still, the ocean's role as a heat sink has helped Earth remain habitable. The planet relies on its oceans not just for life, but for balance. And this balance extends beyond temperature into the chemistry of the seas themselves. Beyond storing heat, the oceans regulate Earth's climate through complex chemical and biological processes. They absorb carbon dioxide from the atmosphere, helping control greenhouse gas levels. Marine organisms use carbon to build shells and tissues. When they die, some of this carbon sinks to the seafloor, locking it away for long periods. This process helps stabilize atmospheric composition over time. The ocean also influences cloud formation, weather patterns, and rainfall. Evaporation feeds storms. Temperature differences drive winds. Everything is connected. The ocean breathes with the atmosphere, exchanging energy and matter continuously. This vast system works quietly, without intention, yet with profound impact. It moderates extremes and supports life across the planet. Earth's climate is not governed by a single force. It emerges from countless interactions between land, sea, air, and life. And as we move from the oceans upward, our attention naturally turns toward water, in another form ice, rain, and rivers shaping the land above. As we move from the open oceans toward colder regions, water begins to behave in an unusual way. Unlike most substances, water expands when it freezes. As liquid water cools and turns into ice, its molecules arrange themselves into a more open structure, taking up more space instead of less. This simple property has enormous consequences for Earth. When water freezes inside cracks in rock, it expands and slowly breaks stone apart. Over time, this process helps turn solid rock into soil, shaping landscapes grain by grain. Expansion also explains why ice floats. Solid ice is less dense than liquid water, so it rises to the surface rather than sinking. This may seem ordinary, but it is essential for life. If ice sank, lakes and oceans would freeze from the bottom up, becoming solid blocks of ice during cold periods. Instead, floating ice forms a protective layer on top, insulating the water below. Life can survive beneath that frozen surface, waiting patiently for warmth to return. From this quiet expansion comes protection, stability, and continuity. And floating ice leads directly to another of Earth's quiet safeguards. Because ice floats, it forms a lid over cold water. This floating layer slows the loss of heat from below, keeping lakes, rivers, and oceans from freezing solid during winter. Beneath the ice, water often remains just above freezing, creating a stable environment where fish, plants, and microorganisms can survive. Life continues quietly under the frozen surface, sheltered from harsh air temperatures above. This insulation also helps regulate seasonal cycles. When ice melts in spring, water warms gradually, preventing sudden temperature shocks to ecosystems. On a planetary scale, floating ice affects climate as well. Ice reflects sunlight back into space, helping cool the Earth. This reflectivity, known as albedo, plays an important role in temperature balance. The presence of ice on water is a delicate balance. Too much ice can cool the planet further. Too little can accelerate warming. Ice is not merely frozen water, it is an active participant in Earth's systems. And while ice protects water locally, the planet's liquid water moves endlessly through a much larger cycle. Among all the planets we have studied, Earth is unique in one crucial way. It is the only known world where liquid water exists stably on the surface, not locked entirely as ice, not evaporated into vapor, but flowing freely across land. This balance depends on temperature, atmospheric pressure, and distance from the sun. Earth sits in a narrow zone where water can remain liquid for long periods of time. Liquid water allows chemistry to become complex. It dissolves substances, transports nutrients, and enables reactions that would otherwise be impossible. Life, as we understand it, depends on this flexibility. Rivers flow, rain falls, oceans circulate. Water moves energy and matter constantly across the planet. Though water exists elsewhere in the solar system, it is usually frozen or hidden underground. On Earth, it shapes the surface openly and continuously. This abundance of liquid water has guided Earth's entire history, from the first life to the present moment, and that water never stays in one place for long. Water on Earth is always moving. Through the water cycle, it travels between ocean, air, land, and living things in a continuous loop. Sunlight warms surface water, causing it to evaporate into vapor. That vapor rises, cools, and condenses into clouds. Eventually, it returns to the surface as rain or snow. Some of this water flows across land as rivers. Some seeps underground. Some is taken up by plants and released back into the air through transpiration. The water cycle redistributes heat, shapes landscapes, and sustains ecosystems. It connects distant regions, allowing moisture from one place to fall thousands of miles away. This cycle has no beginning and no end. It repeats endlessly, adapting to climate, geography, and time. Even the water inside your body once moved through clouds, oceans, and ancient soils. Earth does not store water in one place. It circulates it gently and persistently, and while water is abundant overall, not all of it is easily accessible. Although Earth appears rich in water, most of it is salty ocean water. Of the small fraction that is fresh water, the majority is not readily available. Large amounts are locked in glaciers and ice sheets, particularly in Antarctica and Greenland. These frozen reserves contain most of the planet's fresh water, inaccessible for everyday use. Much of the remaining freshwater lies underground as groundwater. Stored in pores and fractures within rock and soil, this water can be ancient, moving slowly over thousands of years. Only a tiny fraction of freshwater exists in rivers, lakes, and wetlands, yet these visible sources support most human and ecological needs. This uneven distribution makes freshwater precious. It reminds us that abundance does not always mean accessibility. Groundwater feeds springs and rivers quietly from below, sustaining flow during dry periods. Water's hidden presence shapes landscapes just as much as its visible movement. And when water does move across land, it becomes a powerful sculptor. Rivers may seem gentle, but over time, they are among Earth's most powerful forces. Flowing water carries sediment from higher ground toward the sea, reshaping continents grain by grain. As rivers cut through rock, they carve valleys and canyons. The Grand Canyon, for example, was formed by the Colorado River over millions of years. Sediment carried by rivers eventually settles, building floodplains, deltas, and fertile soils. Entire ecosystems depend on this slow redistribution of material. Rivers rarely rush in geological terms. They persist. They follow gravity, responding to uplift and erosion with patience. Even when a river changes course, it continues its work elsewhere, never stopping for long. This quiet persistence connects mountains to oceans, linking distant regions through flowing water. Earth's surface is not carved by sudden force alone, but by constant, gentle motion. And when water freezes in large quantities, its shaping power slows but does not disappear. Glaciers are rivers of ice that move slowly across the land. Though they appear still, they flow under their own weight, reshaping the landscape beneath them. As glaciers advance, they grind rock into fine sediment, carving broad U-shaped valleys and smoothing mountainsides. When they retreat, they leave behind lakes, ridges, and exposed rock. This process unfolds over thousands or even millions of years. Ice advances and retreats in response to climate shifts, leaving lasting marks on the land. Many of today's valleys, lakes, and fjords are the result of ancient glaciers that no longer exist. Glaciers also store vast amounts of fresh water, releasing it slowly as they melt. Though cold and slow, glaciers are powerful architects of Earth's surface. Their presence reminds us that stillness can be deceptive, and beneath both ice and soil, water continues its quiet journey underground. Not all water flows quickly. Groundwater moves slowly through soil and rock, sometimes taking centuries or even thousands of years to travel short distances. Some groundwater was last at the surface during ancient climates, preserved beneath layers of sediment. This water carries chemical signatures of past environments, acting as a record of Earth's history. As groundwater moves, it dissolves minerals, shaping underground caverns and feeding springs and rivers from below. This slow movement provides stability. During dry seasons or droughts, groundwater maintains river flow and supports ecosystems. Because it moves so slowly, groundwater can also be easily depleted if removed faster than it is replenished. It is a hidden system, often forgotten because it is unseen, yet much of life depends on it. Water does not always rush. Sometimes it waits, and where groundwater reaches the surface, it can form another quiet feature of the landscape. Lakes appear calm and permanent, but they form in many different ways. Some are carved by glaciers, others fill volcanic craters. Some develop where rivers change course, or where land sinks along faults. Lakes can be short-lived or ancient. Over time, sediment fills them in, turning lakes into wetlands and eventually dry land. Despite their still appearance, lakes are dynamic systems. They exchange water with rivers, groundwater, and the atmosphere. Their temperatures change with seasons, influencing life within them. Lakes support diverse ecosystems, from microscopic algae to fish and birds. They act as mirrors of climate, responding quickly to changes in temperature and rainfall. Lakes remind us that still water is rarely static, and in the driest places on Earth, water behaves in yet another surprising way. Deserts are defined not by heat, but by lack of rainfall. When rain does arrive, it can be sudden and intense. Dry soil absorbs water poorly, causing rain to run rapidly across the surface. This can create flash floods that reshape the land in hours. Dry riverbeds, called washes or wadis, may remain empty for years, then suddenly fill with rushing water. These floods carry sediment, carving channels and depositing fertile material downstream. Life in deserts is adapted to this unpredictability. Plants germinate quickly. Animals respond rapidly to brief abundance. These rare floods remind us that even the driest landscapes are shaped by water. Earth's systems do not operate in extremes alone. They shift between quiet and intensity. And as water shapes land, the air above it continues its own slow movements, carrying us upward into the atmosphere. As water shapes the land below, air surrounds everything above it. Earth's atmosphere is not a single uniform blanket, but a series of layers stacked gently atop one another. Closest to the surface is the troposphere, where weather happens and where most life exists. Above it lies the stratosphere, home to the ozone layer. Higher still are the mesosphere, thermosphere, and exosphere, each thinning gradually into space. These layers form because gravity pulls gases inward, while heat causes them to expand outward. Temperature changes mark each boundary, creating invisible steps in the sky. Though we cannot see these layers, they influence everything from storms to satellite orbits. The air around you is part of a carefully balanced structure shaped by physics and time. Earth's atmosphere protects life from radiation, burns up meteors, and holds warmth close to the surface. It feels empty, but it is active and alive with motion. And within one of these layers lies a thin shield that quietly guards the planet. High above the ground, within the stratosphere, a thin concentration of ozone plays a vital role in protecting life. Ozone molecules absorb much of the sun's harmful ultraviolet radiation before it reaches the surface. Without this shield, exposure to UV radiation would damage living cells, disrupt ecosystems, and make life on land far more difficult. The ozone layer allows plants to grow, animals to thrive, and humans to live under open skies. Ozone is constantly being formed and broken down through natural processes involving sunlight and oxygen. This balance keeps the layer stable over time. Human activity once disrupted this balance, thinning the ozone layer in some regions. Changes in chemical use have allowed gradual recovery, showing how responsive Earth's systems can be. The ozone layer is not thick. If compressed to surface pressure, it would be only a few millimeters deep. Yet this delicate layer quietly stands between life and radiation, and beneath it, the atmosphere continues to move and mix. As you rise higher above Earth's surface, air becomes thinner. This happens because gravity pulls most atmospheric gases closer to the planet, leaving fewer molecules at higher altitudes. At sea level, air pressure is greatest. With each step upward, pressure decreases, making breathing more difficult for those unaccustomed to altitude. Mountains illustrate this clearly. As elevation increases, oxygen becomes less available, influencing weather, ecosystems, and human physiology. Aircraft cabins are pressurized because the natural atmosphere at cruising altitude would not support comfortable breathing. Pressure differences also drive winds. Air moves from regions of higher pressure to lower pressure, setting the atmosphere in motion. Though invisible, pressure shapes clouds, storms, and climate patterns across the globe. The air around you is always pressing gently inward, a quiet reminder of gravity's reach. And as pressure changes, temperature often changes too, guiding how air moves vertically. In the lower atmosphere, temperature usually decreases as altitude increases. This occurs because air is warmed primarily from the ground upward, not directly by the sun. Sunlight heats Earth's surface. That heat is then transferred to the air above it. As air rises, it expands due to lower pressure, cooling in the process. This cooling affects cloud formation. Warm air rises, cools, and condenses into droplets or ice crystals, forming clouds that drift quietly overhead. Temperature gradients also influence storm development and atmospheric circulation. While this pattern holds in the troposphere, higher layers behave differently, warming or cooling based on absorbed radiation. These vertical temperature changes create structure in the sky, guiding motion and stability. Earth's atmosphere is not random. It follows consistent physical rules, and these rules allow winds to form, carrying air across vast distances. Wind begins with the sun. Because Earth's surface is uneven, land and water absorb heat differently. Some areas warm faster than others, creating temperature differences. Warm air expands and rises. Cooler air sinks. This movement creates pressure differences, and air flows from high pressure to low pressure. This flow is wind, sometimes gentle, sometimes powerful, always responding to heat. Earth's rotation adds complexity. As air moves, it is deflected by the Coriolis effect, shaping global wind patterns. These winds move heat, moisture, and energy around the planet. They influence weather, climate, and ocean currents. Even a light breeze is part of a vast atmospheric system connecting continents and oceans. The air is never still for long, and when wind meets moisture, clouds and storms begin to form. Clouds may look soft and solid, but they are made of countless tiny water droplets or ice crystals suspended in air. As warm, moist air rises and cools, water vapor condenses around microscopic particles called condensation nuclei. These droplets gather, forming clouds. Cloud type depends on altitude, temperature, and motion. Some clouds stretch thin and wispy, others pile high and dense. Clouds reflect sunlight during the day and trap heat at night, influencing temperature. They also carry water across the planet, releasing it as rain or snow far from where it first evaporated. Clouds are not passive. They are active participants in Earth's energy balance. They drift quietly overhead, shaping weather without sound. And when droplets grow heavy enough, gravity draws them back to the surface. Inside clouds, water droplets collide and merge. As they grow larger, gravity begins to pull them downward. When droplets become heavy enough to overcome air resistance, they fall as rain. If temperatures are cold, precipitation may fall as snow or hail instead. Rain nourishes soil, fills rivers, and supports life. Its distribution shapes ecosystems and climates. Some regions receive frequent rainfall, others wait long periods between storms. Rainfall patterns are influenced by geography, winds, and ocean currents. Though rain feels immediate, it is part of a long cycle connecting ocean, air, and land. Each drop may have traveled thousands of miles before reaching the ground. Rain is not random. It follows pathways shaped by Earth's systems. and over time, repeated rainfall can dramatically alter landscapes. Weather describes short-term conditions. Climate describes long-term patterns. A single storm is weather. Average rainfall over decades is climate. Weather can change quickly. Climate shifts slowly, shaped by large-scale processes. Climate influences ecosystems, agriculture, and human societies. It sets the backdrop against which daily weather unfolds. Earth's climate has changed many times, driven by shifts in orbit, atmosphere, and geology. Understanding this difference helps us see patterns beyond the moment. Weather may surprise us. Climate tells a longer story. Both are real, both matter, and both depend on energy arriving from one source above all others. Nearly all energy in Earth's climate system comes from the sun. Sunlight warms land, water, and air, setting everything in motion. The amount of energy received varies by latitude, season, and time of day. This uneven distribution drives winds, ocean currents, and weather patterns. Earth's tilt creates seasons, changing how sunlight strikes the surface throughout the year. The planet reflects some sunlight back into space and absorbs the rest. This balance determines temperature. Small changes in energy flow can lead to large shifts over time. Though the sun feels constant, its influence shapes every aspect of Earth's climate. Without it, motion would stop, water would freeze, air would settle. And while the sun provides energy, Earth's surface responds in complex ways. Not all surfaces absorb sunlight equally. Dark surfaces like forests and oceans absorb more energy, warming quickly. Light surfaces like ice and snow reflect more sunlight back into space. This reflectivity is called albedo. High albedo cools. Low albedo warms. As ice melts, darker surfaces are exposed, absorbing more heat and accelerating warming. This feedback can amplify change. Vegetation, soil, and water all influence how energy moves through the climate system. Earth's surface is a mosaic of reflectivity, constantly changing with seasons and climate. These interactions help regulate temperature, but they can also magnify shifts. Energy moves in cycles, guided by surface and sky alike. And as sunlight interacts with Earth's surface, life itself becomes part of the system. As sunlight interacts with land and water, life quietly reshapes the air itself. Earth's atmosphere has not always been what it is today. Early in the planet's history, oxygen was scarce and the air was filled with gases hostile to most modern life. The transformation began with tiny organisms in ancient oceans. Through photosynthesis, they released oxygen as a byproduct. Over millions of years, this oxygen accumulated, changing the chemistry of the atmosphere. This shift allowed new forms of life to emerge, including complex, multicellular organisms. Oxygen enabled efficient energy use, supporting larger bodies and more active lifestyles. Life did not simply adapt to the atmosphere, it created it. Even today, plants, algae, and microbes continue to regulate gas levels, exchanging oxygen and carbon dioxide with the air. The atmosphere you breathe is partly a biological creation, shaped by countless generations of living things. Earth's air is alive with the imprint of life, and within that living atmosphere, ecosystems spread across the surface. No ecosystem exists in isolation. Forests, oceans, grasslands, and deserts are linked through air, water, and living movement. Seeds travel on winds. Nutrients flow through rivers. Animals migrate across continents and oceans. Even dust from distant deserts can fertilize forests thousands of miles away. These connections mean that changes in one place can affect life far beyond its borders. A shift in ocean temperature can alter weather patterns on land. Loss of vegetation can influence rainfall elsewhere. Earth functions as a network, not a collection of separate parts. This interconnectedness adds resilience, but also sensitivity. Balance depends on many small interactions working together. Ecosystems quietly communicate through shared cycles of energy and matter. Life moves across boundaries effortlessly, responding to opportunities and constraints. And as ecosystems connect across the surface, life also changes the ground beneath them. Soil may appear lifeless, but it is shaped by living organisms, especially plants. Roots penetrate rock and sediment, breaking material apart and anchoring loose particles. As plants grow and die, their remains add organic matter to the ground, enriching soil with nutrients. Microbes and fungi further break down this material, creating complex, fertile layers. This living soil supports new growth, allowing ecosystems to persist and expand. Without plants, soil erodes quickly. Wind and water carry it away, leaving land barren. Roots also help retain moisture, regulate temperature, and support underground life. Soil formation is slow. It can take hundreds or thousands of years to build just a few centimeters. Earth's landscapes depend on this quiet cooperation between rock, water, and life. And within soil, another hidden network works tirelessly beneath the surface. Beneath forests and grasslands lies a vast web of fungal threads known as mycelium. These networks connect plant roots, allowing resources to be shared across entire ecosystems. Through these connections, plants can exchange nutrients, water, and chemical signals. Older plants may support younger ones. Stressed plants can warn neighbors of threats. This cooperation increases resilience and efficiency, helping ecosystems adapt to changing conditions. The network operates quietly, without central control. It grows, shifts, and responds based on local interactions. Fungi play a key role in nutrient cycling, breaking down organic matter and making minerals available to plants. What appears above ground as separate trees and grasses is often united below. Life extends beyond what we can see, and as plants and fungi shape the land, animals add their own movements and influences. Animals play a crucial role in spreading life across Earth. As they move, they carry seeds on their fur, feathers, or within their digestive systems. When animals travel, seeds travel too, reaching new environments where plants can grow. This movement expands ecosystems and maintains genetic diversity. Animals also redistribute nutrients. Through feeding and waste, they move materials across landscapes, enriching soil and supporting plant growth. Even small creatures contribute. Insects pollinate plants. Burrowing animals aerate soil. These actions are not deliberate acts of planning. They are natural consequences of survival and movement. Life spreads itself through motion. Animals connect ecosystems through their daily activities, linking forests to grasslands, land to water, and through these interactions, Earth's surface becomes more alive and diverse. As animals move and shape ecosystems, they must adapt to the planet's rhythms. Earth spins steadily on its axis, completing one rotation roughly every 24 hours. This motion creates the cycle of day and night. As Earth turns, different regions face the sun or move into darkness. Light and warmth alternate predictably, shaping biological rhythms. Life evolved around this cycle. Plants open and close leaves. Animals wake and rest. Human bodies follow internal clocks aligned with daylight. Earth's rotation is smooth and constant, rarely changing. It provides stability amid other shifting systems. Without rotation, one side of the planet would face constant sunlight, while the other remained frozen in darkness. Day and night allowed temperature regulation, rest, and renewal. The cycle feels simple, but it underlies nearly every biological process. And beyond daily rotation, Earth's movement through space adds another layer of rhythm. Earth's axis is tilted about 23 degrees relative to its orbit around the Sun. This tilt causes seasons. As Earth travels through space, different hemispheres receive varying amounts of sunlight throughout the year. When one hemisphere tilts toward the Sun, it experiences summer. The opposite hemisphere experiences winter. This change affects temperature, daylight length, and weather patterns. Seasons shape migration, plant growth, and human activity. They guide agricultural cycles and ecological rhythms. Without Earth's tilt, seasons would not exist as we know them. Climate would be more uniform, but less dynamic. The tilt remains stable over long periods, providing predictability. Earth's orbit and tilt work together, creating repeating patterns that life has adapted to over millions of years. And over much longer timescales, even these rhythms slowly change. Earth travels around the Sun in an orbit that is nearly circular. The distance between Earth and the Sun changes only slightly throughout the year. This means seasons are not caused by distance from the Sun, but by axial tilt. The stable orbit helps maintain consistent energy input, supporting long-term climate stability. Small variations in orbit do occur over tens of thousands of years. These changes influence climate cycles, including ice ages. Earth's path through space is steady and predictable, shaped by gravity. The planet does not wander randomly. It follows a quiet curve around its star. This consistency has allowed life to develop and persist, and as Earth moves through space, it carries its magnetic shield along with it. Deep beneath Earth's surface lies a molten outer core made primarily of iron and nickel. As this liquid metal moves, it generates Earth's magnetic field. This field extends far into space, forming a protective bubble called the magnetosphere. It deflects charged particles from the Sun, shielding the atmosphere from erosion. Without this magnetic protection, Earth's air could slowly be stripped away, as has happened on some other planets. The magnetic field is dynamic. It shifts, fluctuates, and occasionally reverses direction over geological time. Compass needles align with this invisible force, allowing navigation. Though unseen, the magnetic field is essential to life as we know it. Earth's interior quietly protects its surface, and that interior continues to release heat upward through the crust. Earth formed hot, and it has been cooling ever since. Even now, heat slowly escapes from the planet's interior. This heat comes from leftover energy from formation and from radioactive decay within the mantle and core. As heat rises, it drives mantle convection, plate tectonics, and volcanic activity. Geothermal energy warms hot springs and fuels hydrothermal vents. Though invisible, this internal heat keeps Earth geologically active. The planet is not cold and dead inside. It is warm, dynamic, and moving. Heat connects the deep interior to the surface, shaping landscapes and sustaining processes. Earth is alive with motion, both above and below. And as internal heat meets surface life, the planet continues its long, quiet story. Earth is ancient beyond ordinary imagination. Scientists estimate that our planet formed about 4.54 billion years ago, coalescing from dust and gas orbiting a young sun. In those early moments, Earth was molten and chaotic. Impacts were common. Heat dominated everything. Slowly, the surface cooled, oceans formed, and the crust stabilized enough for long-term change to begin. This immense age means that everything familiar is relatively new. Mountains rise and erode, oceans open and close, species appear and disappear, yet Earth remains. Most of its history unfolded without animals, plants, or even oxygen-rich air. Life, when it emerged, was microscopic and patient. The planet does not hurry. Billions of years pass quietly beneath every step you take. Understanding Earth's age stretches our sense of time, inviting calm rather than urgency. And within this vast span, Earth has endured many dramatic changes. Over its long history, Earth has experienced several mass extinction events. These were periods when a large percentage of species vanished in a relatively short time. Some extinctions were caused by volcanic activity, others by climate shifts or asteroid impacts. The most famous ended the reign of the dinosaurs. Though devastating, these events did not end life. Instead, they reshaped it. Surviving organisms adapted, diversified, and filled newly opened ecological roles. Life proved resilient, returning in new forms after each disruption. Mass extinctions remind us that Earth's surface life is dynamic, not permanent. Change is woven into the planet's story. Even after great loss, ecosystems rebuild slowly, guided by evolution and time. The planet does not cling to a single arrangement, it moves forward, and sometimes these changes are recorded quietly in stone. Rocks are Earth's memory. Layer by layer, they record ancient environments, climates, and life forms. Sedimentary rocks form as particles settle over time, trapping fossils and chemical signatures. Each layer represents a different chapter. By studying rock formations, scientists can reconstruct past oceans, forests, and atmospheric conditions. Even mountain ranges reveal their origins through folded and fractured stone. Rocks do not speak, but they hold stories billions of years old. Some minerals form only under specific temperatures and pressures, offering clues about Earth's interior and surface conditions long ago. This slow accumulation of evidence allows us to read Earth's past with patience. Every cliff face is a timeline, every canyon is a record, and just as rocks preserve history, Earth's surface is continually reshaped by erosion. Erosion is Earth's quiet sculptor. Wind, water, ice, and gravity work constantly to wear down rock and transport material elsewhere. Mountains rise through tectonic forces, but erosion slowly lowers them. Rivers carve valleys, waves shape coastlines, glaciers grind stone. This process is gentle on human timescales, but immense over millions of years. Erosion balances uplift, preventing Earth's surface from becoming too extreme. It creates fertile plains from ancient mountains and redistributes nutrients across continents. Even the hardest rock eventually yields. Erosion reminds us that nothing remains unchanged forever. The land beneath your feet has traveled far, carried by wind or water from distant places. And through erosion, Earth continuously renews its surface. Soil is more than dirt. It is a living system that stores large amounts of carbon. Plants absorb carbon dioxide from the atmosphere during photosynthesis. When plants die, some of that carbon becomes part of the soil. Microbes break down organic matter, cycling carbon slowly back into the air or deeper into the ground. Healthy soils can store carbon for long periods, helping regulate atmospheric levels. Disturbing soil can release stored carbon, altering climate balance. Soil connects life, air, and rock in subtle ways. It supports plants, filters water, and feeds countless organisms. This thin layer covering Earth's surface plays an outsized role in planetary stability. And as soil forms and erodes, living systems adapt and respond. Life on Earth exists within a surprisingly thin zone called the biosphere. It extends from deep underground to high in the atmosphere, but relative to Earth's size, it is delicate. Most life is concentrated near the surface, where conditions are stable. Despite its thinness, the biosphere wraps around the entire planet, touching land, sea, and air. Life adapts to extremes, from deep oceans to frozen tundra, but always within narrow limits. This fragility makes life both resilient and vulnerable. Small changes can have large effects across interconnected systems. The biosphere is Earth's living skin, and within this skin, countless species interact quietly every moment. Ecosystems with greater biodiversity tend to be more stable. Many species performing similar roles allow systems to adapt when conditions change. If one species declines, others may fill its role, maintaining balance. This diversity spreads risk and supports resilience. Biodiversity also enhances productivity, nutrient cycling, and adaptability. It emerges slowly through evolution, shaped by time and environment. Loss of biodiversity reduces flexibility, making ecosystems more vulnerable. Each species contributes in ways that may not be immediately visible. Life thrives through cooperation and variation, and over time, biodiversity reflects Earth's long evolutionary history. Evolution is not a sudden process. It unfolds gradually as small changes accumulate over many generations. Traits that improve survival or reproduction become more common over time. This slow adjustment allows life to respond to changing environments. Evolution does not aim or plan. It follows opportunity and constraint. Over millions of years, it produces remarkable diversity. The forms of life around you are temporary expressions of an ongoing process. Change is constant, even when it is imperceptible. And evolution links the past to the present without interruption. The continents have not always been where they are today. Over Earth's history, they have merged and separated repeatedly. At times, all land formed a single supercontinent. At others, continents drifted far apart. These movements altered climate, ocean circulation, and evolution. Land bridges formed and vanished, allowing species to migrate or become isolated. Continental motion is slow but persistent. Earth's surface reorganizes itself over deep time. The map of today is temporary, and these rearrangements continue even now. Earth functions through cycles that repeat over vast timescales: carbon cycles, water cycles, rock cycles. Matter moves between forms, places, and states. These cycles create stability through motion. Nothing is truly lost, it is transformed. The planet maintains balance through continuous change. Understanding these cycles helps us see Earth as a living system rather than a static object. Time moves slowly here, measured in layers and loops, and as these cycles continue, Earth carries us toward the present moment. From where you sit or lie, the Earth feels solid and unmoving. But beneath that sense of stillness, change is always underway. Continents drift, mountains rise and wear down, oceans circulate. The planet reshapes itself without pause. Most of these changes are far too slow to notice. A river may shift only a few grains of sand in a day. A tectonic plate may move no more than your fingernail grows in a year. Yet, over time, these small motions accumulate into transformation. Earth does not rely on sudden force alone, it relies on patience. Even the air above you is moving, adjusting to heat and pressure. Even the ground beneath you carries the memory of past oceans, forests, and creatures. Nothing on Earth is fixed forever. Stability comes from continuous motion, not from stillness. This quiet activity gives the planet resilience. It allows recovery, adaptation, and renewal. And as Earth changes, it carries the marks of everything that has ever lived upon it. Earth holds memory not in thoughts, but in structure. Ancient shorelines remain etched into stone. Fossil reefs rest far inland. Glacial scratches mark mountains that once lay beneath ice. Chemical signatures preserved in rock record ancient atmospheres and oceans. Isotopes reveal past temperatures and climates. Layers of sediment quietly stack time into visible form. Even living organisms carry memory. DNA holds echoes of ancient adaptations. Behaviors reflect environments long gone. The planet does not forget. It stores its history patiently, layer by layer. This memory allows scientists to read Earth's story, but it also shapes the present. Past events influence today's landscapes, ecosystems, and resources. You walk across pages of deep time without seeing the text beneath your feet. Earth's past is not separate from its present. It is woven into it, and this continuity gives the planet a remarkable sense of endurance. Despite constant change, Earth has remained suitable for life for an astonishing length of time. For billions of years, temperatures stayed within a range that allowed liquid water to exist. This stability did not come from stillness, but from balance. Feedback systems adjusted heat, chemistry, and circulation as conditions shifted. When the sun grew brighter, Earth compensated through atmospheric changes. When volcanic activity increased, weathering and oceans responded. The planet regulates itself through interconnected processes that dampen extremes over long periods. This does not mean conditions were always gentle. Earth has known ice ages, hothouse periods, and dramatic upheavals, yet life persisted. Habitability is not perfection, it is resilience. Earth's ability to remain livable is one of its most remarkable qualities, and life, in turn, has helped maintain that balance. Life is not merely a passenger on Earth, it actively shapes the planet. Plants regulate gases in the atmosphere. Microbes cycle nutrients through soil and water. Coral reefs alter coastlines. Forests influence rainfall patterns. Over time, living organisms have transformed rock into soil, altered the chemistry of oceans, and changed the composition of the air. Earth and life exist in partnership, each responding to the other. This relationship is dynamic. As environments change, life adapts. As life adapts, environments shift again. Neither acts alone. The planet you experience today is partly a biological creation. This reciprocity has allowed complexity to emerge gradually, layer by layer. And within that complexity, Earth has supported an extraordinary variety of forms. From deep-sea microbes to towering forests, Earth supports a staggering range of life forms. Each species occupies a niche shaped by temperature, moisture, chemistry, and time. Some life thrives in heat, some in cold, some in darkness, others in constant motion. This diversity reflects Earth's varied environments and long history of evolution. No single form dominates everywhere. Life adapts locally, responding to conditions with creativity and constraint. Even the smallest organisms play essential roles, forming the foundation of food webs and cycles. This richness is not random. It emerges from countless interactions over deep time. Earth's diversity is a living expression of its complexity, and this living network extends across land, sea, and sky. Earth does not exist in isolation. It moves through space as part of a solar system shaped by gravity and time. The Moon influences tides and stabilizes Earth's rotation. The Sun provides energy. Other planets affect orbital rhythms subtly but persistently. Earth formed from the same materials as the rest of the solar system, forged in ancient stars. Meteorites still fall, carrying fragments of early history. Cosmic cycles influence climate, geology, and evolution over long timescales. The planet is both unique and connected. Understanding Earth means understanding its place among other worlds. And within this vast context, Earth remains a small but remarkable place. Earth systems are resilient but not rigid. Balance is maintained through movement and adjustment, not stasis. When one process intensifies, others respond. Heat drives circulation. Circulation redistributes energy. Chemistry adjusts slowly. This dynamism allows recovery after disruption. Earth has endured impacts, eruptions, and extinctions, yet continues. Balance here is not stillness. It is flow. Understanding this helps us see change not as failure, but as function. The planet is not easily broken, but it is responsive. And responsiveness is what has allowed it to persist. Human lives unfold over decades. Earth's processes unfold over thousands, millions, and billions of years. Mountains rise slowly. Continents drift imperceptibly. Climate shifts over generations. This difference in scale can make Earth seem unchanging, when in reality, it is always in motion. Recognizing these timescales invites patience and perspective. The planet does not rush. It does not pause. It continues. Your moment exists within a much larger story, and within that story, Earth carries everything gently forward. Long after individual lives pass, Earth will continue its processes. Rivers will flow. Plates will drift. Life will adapt. The planet has no end point. It responds to conditions as they arise. Future Earth will not be identical to today's, just as today's Earth differs from the past. Change is not loss. It is continuity. Earth's story extends far beyond any single chapter, and that long perspective offers calm rather than urgency. Earth is old beyond measure, yet alive with motion. Its age does not make it static. Its longevity comes from change. Fire moves beneath the crust. Water circulates endlessly. Air shifts and settles. Life grows, adapts, and responds. The planet is not a backdrop. It is an active participant in its own story. You are part of this system, shaped by it, and contributing to it simply by existing. Earth carries you gently, spinning through space, wrapped in air and water. It has done this for billions of years, and tonight it continues quietly, steadily, without effort. And now, as these quiet facts settle, let your thoughts grow still. The Earth continues its slow turning, carrying oceans, mountains, and you. Nothing more is required. Just rest, breathe, and drift. The story goes on softly, even as you sleep.